Good afternoon, everyone. I'm Silvia Rossi, associate professor from the University of Naples Federico II, and I'm associate professor at the academic degree of computer science. So here today, I thought it would be nice to talk about personalization and adaptation in robotics. And I think that also other talk will somehow cover this topic. But in my presentation, we will talk about this topic in the framework of a particular kind of robots that are personal robots. So robot that we foresee in the future could be easily bought by everyone. They could be available in each house. But we are not there yet. So even though we are seeing a lot of very nice hardware, even with cheap prices, like the one depicted in the slides, we don't have that. These robots are now both a lot in the market. So we have also a lot of company, I would say, that started to build this kind of robots, and then they failed, so they have to close their job. So in our opinion, what's the gap that is missing? So what are the features that are missing on this kind of robots that makes them not yet ready to be available and to be used in the market? I would say it's they are called personal robot, but they intend personal as domestic one. They don't intend personal as be able to be personalized and customized with respect to the needs of each single user. So it's a very huge concept, because of course for us personalization is something that makes the robot easily adapt to our own needs, our own preferences. So just think about your mobile phone. So you have your mobile phone, and if you try to compare the one of your friend, maybe it's the same brand of mobile phone, it's the same type of phone, but then if you see, for example, the app that are installed on the other phone could be completely different from your own. So what makes the phone your personal phone is the capabilities, the application, the thing that are installed on the phone that make difference from another one. So that's the idea that we have in the future. So being able to somehow have this vision where the behavior or the capabilities of a personal robot could really be personalized and adapted with respect to the specific users. Actually, this kind of idea, we are fostering them in a European project that is a training network where that's called Perseo. That's the European Training Network on Personalized Robotic as Service-Oriented Application. So in this project, we are trying to understand, first of all, what are the capabilities that a robot needs in order to understand its own user. Because, of course, we want the user to be able to personalize the robot, but we want also the robot to be able to do it autonomously. So understanding, for example, its surrounding, how to interact with the user. And so once that we are able to understand the external context, the robot should be able to personalize its behavior. And this should be done in an easy way, like a plug and play application that we have on our mobile phone. So when talking of personalization in this domain, there are actually 4 things that we have to consider. First of all, we talked about who is the user. So how much my individual differences will shape the application that I'm using on my robots with respect to the one used by another one. So we need to understand how to make the so-called user model for the robot. Actually, the concept of user model, it's a very well-known concept in other domains, for example, in general human-robot interaction or human-machine interaction or recommender systems. So there are a lot of other disciplines that have a lot of background on how to model the user and how to use relevant information on the user to adapt the behavior. And so why not, for example, fostering by taking inspiration by the other discipline in order to have our robot able to model the user, but also what to personalize. So, for example, we could be able to personalize what to do, like making this function with respect to another function. So one application with respect to another application, but also how to do it in the sense that I can accomplish, especially if I'm a physical robot that moves in the space, I can accomplish the same task, so the same function, in different ways. So be able also to understand what are the characteristics of execution of a task that could be adapted and personalized. It's important. And also when to have this kind of personalization, because in physical interaction or interaction with a robot, also the temporal dimension has an effect, has an impact. So I'm going to start to put you some context, and I'm going to start with this picture that's taken from a very nice review on user adaptive interaction made by Martin Santos and Diaz, that shows somehow how we can adapt the behavior of robot with respect to a user, and also in the case of additional information we have to the user. So the easiest way, actually, I will call it the reactive way, is simply a closed loop. So we have a user interacting with the robot. So in this picture, we have a user interface, but could be the user interface of the robot. So we have that the user interact with the robot, and then with respect to the perception that we have on the user, we have some pre-coded parameters of the behavior, and so we can reactively adapt the behavior of the robot with respect to the user that we have in front of us. So everything somehow is pre-coded in the so-called operational parameters that kind of shape the reaction of the robot or shape the decision-making process of the robot. A second approach, I would say that the first approach is the one that is used almost by everyone. So many of the applications you may find in the literature and in the robots are, of course, made in this way because it's the easiest way, also the more robust way, because you have mainly a reactive application. Then, in this second example, we are doing something different. So instead of closing the loop with respect to what we perceive by the user, let's just think about having a model of the user. So a model is something that we have a priori, that somehow describe how the user behave, what are his preferences, a lot of things that we can model before the interaction. That still we have the operational parameters that told us how to change the decision making with respect to a specific user model or a specific instance of the user model. And then with this information, the robot or the interface decide what to do from time to time. So that's a second approach where we have like a predefined user model. And then, of course, the most complex one, it's something that put the first two together. So we do have operational parameters to modify the decision-making and the behavior of the robot. We do have a description of things that we know about the user, so we do have a user model, but we are also able somehow to update this model. So using the reaction, the feedback of the user, update this model and use this updated model to decide what to do. So these are the main three approaches that we can find in the literature. So of course, the most complex is the last one. And in this talk, you will see some of example of application that use one of these three approach. And in particular, you will see example in real-world application in the context of project that we had here at University of Naples. So, as I said, let's start with the project. So, of course, the first thing, if we have to provide an adaptive system, we have to start from the users. So, who are the users, and what are the characteristics that make them different with respect to other class of users, and what are the characteristics that make user in the same class different one from another. So in this project, for example, we were dealing with elderly people, and in particular, we were dealing with elderly people with mild cognitive impairments, like, for example, Alzheimer's disease in the first stage of the disease. And so we started from a specific population of user, and we start to analyze the characteristics and the main relevant parameters that could be used to adapt the behavior of the robots. And so let's start from very simple adaptation. As I told you, the simplest way to adapt the robot behavior is a reactive adaptation with respect to the perception of the robots has with respect to the user. And here, in particular, the goal of the robot was to provide help in monitoring the behavior of the user. So the robot was intended to be used, for example, as a monitor technology. So something whose main goal is not really to interact, is not really to do anything else, but just to monitor the behavior of the user and to understand if something goes wrong and there is need of an intervention. And of course, this kind of goal, it's very tricky because there is not really interaction with the user. So somehow the user may feel like a passive entity with respect to the robots, because he or she do not feel the necessity, the needs of having the robot monitoring the behavior. And so the behavior of the robot has to be carefully adapted in order to be, for example, less intrusive as possible. We don't want a robot to follow you the whole time. And so the behavior has to be adapted in order to be not to cause discomfort. And this is very specific for a single individual, because our perception could different from another one. And indeed, since we want to have a monitor technology, we always talk about the ability of having a lot of Internet of Things, of sensors, of things that we can put in the house, so we can have continuous data on what the user is doing, etc., etc. So that's our labs, so how we imagine that the future house will be. But indeed, the reality is kind of different. So when we want to develop something and we want to test these things in real settings, in real environment, we have to deal with a lot of problems, and we have to deal with the possibility of not even having Wi-Fi in the environment. So we will have just, for example, to rely on the robot's behavior, and that's it. So that's why in some cases, a very reactive approach could be a solution. Moreover, we say that we can adapt different things. And so what to adapt could also be modeled, for example, with respect to whether an adaptation would be starting in the physical context. So, for example, adaptation regarding the physical movement or the physical interaction of the robot with the user. But also, since we are dealing with the patient with cognitive disease, we may have also the necessity, for example, to interact in a cognitive way. So also understand how to change the way that the robot is interacting, for example, using natural language or whatever else modality to the user in the best way. And also how to adapt eventually things that are modeling the social behavior of the robot. So it's not only what to do, but how to do it, as I said at the beginning. So for example, very small changing in the how, for example, the robot moves or the robot display social cues may change the perception of the robot itself. So I want to show you this very first example. It was a work made 10 years ago in the context of a project called DexSmart. And here we have a very simple manipulator dealing with the task of picking and places object and passing object to the user. And also in this very simple scenario, we can have that the behavior of the robot can be adapted with respect to what perceived in the human. So for example, if the robot see very quick movements on the human, the robot should be able to modify its speed or its trajectory in order, for example, not to cause discomfort or not to make the human feel less safe because the robot is moving too fast. Or if the user, like in this case, is not looking at the robot should eventually stop, because if the user is not aware of the movement, it again could be perceived as not safe interaction. So in this case, the speed and especially the speed, especially, it's modified with respect to what we adapt, with respect to what we perceived on the user. Also, if we have a robot moving around, we are also expecting that somehow he will move and share the space with us in an intelligent way. So it's like we don't want to have a very annoying neighborhood that stay too close to us or stay always with us. So whenever the robot has to move around and, for example, stop at some distance in order to monitor our behavior, we would like that the distance is taking or the trajectory is taking respect some kind of social rules. So, for example, in psychology, in human interaction, there were defined these different spaces where we have the closest space. It's called intimate space. So it's something that defines our own space, and we don't want anyone be in this space because it's our space. And then we have a personal space where somehow we can allow people that are really close to us, or we have the social space, that's typically the space where we are comfortable in having social interaction, and then there is this other space. So that was how the spaces were defined regarding human-human interaction. But what about human-robot interaction? So in a human-robot interaction, we can somehow think that these spaces change a little bit. And we started to understand, for example, what if we have a user model, and this user model, for example, includes some data about the personality of the user. And in this case, we can use this user model in order to change how the robot behaves, how close the robot approach the user in order, for example, to monitor the user. And in this case, what we found, of course, that there are two specific traits of personality, for example, neuroticism and openness, that somehow really shape how the distances from a robot are perceived with respect to the user. For example, a user with a very low neuroticism allows the robot to come close. The same is a user with a high openness. But it's not just like that, because in human-robot interaction, we can have also that the user may be doing something. So it's not we have two human beings standing in front of each other, but we may have, for example, me sitting or me lying or whatever else. So what if we also are able not only to rely on a specific user model, but we are able to understand the current situation. So we are able to also perceive the current situation and to adapt the behavior of the robot with respect to the current situation. So for example, in this case, we found out that in case of lying and sitting pose, the user are more comfortable with a robot come closer with respect to the fact that I may be standing or I may be walking. So in this case, I prefer a larger distance to the robot. And so, for example, in this simple experiment, we had the robot controlled by a network, actually was a fuzzy Bayesian approach, where the data were the user model in terms of personality, the current pose of the user, and these two actually modified the decision-making process of the robot in order to understand what are the distances to be taken from the user in order to monitor them and not causing discomfort. But it's not just that we are sitting or it's not just that we are standing. What is important is actually what we are doing. For example, if I'm watching TV, of course, I don't want a robot just start walking in front of me and occluding my field of view. So it's not just my pose, it's what I'm doing that modify the perception I have of the robot. So the robot should be able somehow to understand what I'm doing and to adapt again, consequently, with respect to the user. And also, so we started to considering, for example, sitting pose or standing pose, because we saw that there were these two groups of different approaching distances. And for each pose, we considered different activities, and in particular, different activities that require a lot of attention in doing the activities. For example, if I'm ironing, typically Italians ladies are very skilled in this kind of task. So they really do need to put a lot of effort. It's like going in bicycle. They know what they are doing. So this kind of task require very low cognitive attention with respect to the task itself. But for example, if I'm working on the computer or I'm talking to the phone, these activities are more requiring attention by myself. So eventually the presence of the robot should be adapted with respect to this factor too. So in order to recognize what the user are doing, it was 4 or 5 years ago, we started with this kind of research. So let's say it was before the use of transformers that somehow combine the different feature within an input. So we were trying to understand how to get data from skeleton and use this data to get relevant information. And since this data somehow are linked one to each other, because we know that joints somehow are linked in a particular position with respect to the physical body, we wanted to understand how to model this data, and to model this data in order that, for example, a convolutional neural network could take the advantage of the local relationship among the joints in order to make a better recognition of the specific activities. And in this sense, we come out with a representation of the full body as an image where the the joints and the position of the value of the joints were nearby other joints that are connected somehow in the real body. So for example, here we have the two arms nearby, then we have the torso, and then we have the legs and so on. So with this kind of approach, we were able to take advantage of convolutional neural network and also, for example, long short-term memory layers to understand what a person was doing. And this kind of approach have very good performance, for example, in a very well-known data set dealing with activity recognition. So once that we have this data, so once that we are able to recognize what a user is doing, again, we can use this information and adapt the robot behavior consequently. So this time when we know what the user is doing, it's not just a matter of keeping the proper distance to the user, but it's also a matter of getting the good trajectory, the allowed trajectory to approach the user itself. Indeed, this is also can be done in a very reactive way with some geometrical information with respect, for example, the shoulder of the user. We can recognize what the user is doing, and we can compute in a reactive way the proper trajectory to approach the user. For example, here you can see in the video that the robot is looking for the user, and once he found the user and he recognized the user, recognized his pose and recognized his activity, he will start to make the proper trajectory in order to approach the user itself. So he's still wandering around in this video. So it's not recognized the user yet. Now he found the user, so it's computing the activity recognition, it's computing the trajectory, and then in a reactive way it's moving in order to, for example, in this case, the proper approaching direction would be like 45 degrees or lateral approaching, because the user is watching TV. And so the robot, while continuously monitoring with the head the specific position of the user, it's computing the trajectory to approach the user and also the proper distance to stop and monitoring the user. So this could be done, for example, with Pepper, but could be done also with very simple robots, because this kind of approach actually not depends on the specific robot capabilities. So in this case, you see a very simple robot that just made by a turtle bot, so a Roomba-like robot with a computer and a Kinect. So in this case, again, the robot is wandering around in order to search for the user. And eventually it will find the user and compute the proper approaching direction and starting it. So when this kind of approaching it's made in a reactive way, then also very simple robots are able to handle this kind of adaptivity. Well, this is also important for another reason, because typically in human-robot interaction, we are used to have the robot and the user face-to-face and interacting one to each other. So in this case, we have that the robot somehow has a very nice view of the user, because the user is just in front of the robot. And so the ability to elaborate, to get the data from the user and to compute for example, the information of the body pose, it's very simple. But what if the main goal of the robot is not to interact with the user, but for example, to going around and cleaning the house? So in this case, we are expecting that the robot do not have a very good view of the user itself. The user may be not even in his field of view. So in this kind of task, actually, the correct perception of the user and to understand what are the important data to adapt to, it's very challenging because we have data that change, that are taken from different angles. So understanding how to make this kind of adaptation and what is the data we need for making this kind of adaptation, it's very challenging. So for example, in the cases we saw before, so in cases of a robot monitoring a user, we could be interesting, for example, to understand if the user is getting discomfort by the presence of the robots. Or, for example, if the user is doing something for which he or she do not want to be interrupted. So understanding this kind of conflicts between what the user is doing or what the robot is doing, it's challenging, as I said, because the view of the robot may be changing during the day. And so we want to be able to understand how to, what are the cues that really characterize the behavior of the user, and in particular, for example, is discomfort or disengagement in the case that we are not face-to-face. So how to recognize the cues of disengagement, for example. We thought that could be a starting point, starting indeed trying to recognize the cues that characterize the opposite phenomena. So, for example, the engagement. So typically in human-robot interaction, the robot should be able to understand if the user is engaged in the interaction. And typically when you evaluate the engage, what you evaluate? You evaluate the body pose, you evaluate where the user is looking, for how long, his gazes around, and stuff like that. So we thought, okay, let's try to understand if the same feature that were typically used for engagement can be used also for recognize, for example, discomfort and disengagement. And so we wanted to rely to understand the so-called nonverbal communication cues. So we made some experiments, and we try to understand if somehow the bad and limited view that the robot has of a user could be enough for measuring, for example, discomfort and disengagement. And we actually discovered that also in this case, for example, the recognition of the activity and the recognition, for example, of head pose, of gazes, their duration in time, body posture could be an index of engagement, but also of disengagement. So at the end, what we would like to have, it's, for example, a trajectory, so the ability to modify, to adapt the trajectory and the distances of the robot that takes into account everything. So it takes into account the user model, for example, in terms of personality. You should take into account what the user is doing, so its pose and its activity, but at the end also adapting in a reactive way to the stimuli. So you remember the three picture we saw at the beginning. So we have a model, we adapt to the model, but we should be able also to recognize the things in an online way and to use this information to modify the model, to adapt to the model. And so we end up with an reinforcement learning approach where the online evaluation of the discomfort of the user when the robot is approaching the user could be used to modify and update the user model, so how to behave in the presence of this specific user. So, changing a little bit of context, if we are able to understand the behavior of the user from nonverbal cues, so in which other domain we can have this kind of adaptation? We thought that another domain where the impact of a robot or a personal robot adapting itself could be of relevance, it's, for example, in hospitals. So what you have in hospital, of course, you have children that typically have a lot of medical procedure, long procedure to be taken, and they could be in a pain mode, they could have a lot of anxiety, so why not to try to use robot there in order to distract them, in order to make their experience less painful. And so we started from the idea that also, for example, the pain and discomfort of the anxiety of the user could be understood from behavioral cues. And also in this case, we started from some very well-known scale that typically the nurses use to evaluate the anxiety of a person with respect, for example, its movements of the face, of the leg, whether he's crying or not, and to use this feature to make an automatic assessment of the level of anxiety of the children. And so once we have this information, the behavior of the robot can be adapted. And in this case, of course, it's not the trajectory of the robot that can be adapted in a reactive way, but it's the emotional behavior of the robot. So why we want to adapt the emotional behavior of the robot? Because in the case of very high anxiety, typically people are less inclined to be distracted. So if I'm really worried about something and a nice robot can, hey, come play with me, probably I don't care. So if he got very different emotional behavior, probably it could be enough to catch my attention for a while and then get me engaged in interaction. So in this case, the adaptation it's made starting from the anxiety level of the children, and will produce different personality of the robot itself. So we had some tested with this kind of approach. We had first a pre-testing in a vaccination center. It was pre-COVID, so it's not really a particular stressful situation for the children, but indeed, if the children are relaxed, it's also better for the nurses. So we had this robot in a real vaccination center and interacted with the children waiting for the vaccination, and we really had that the behavior as perceived was really more calm at the end if they were interacting with an adaptive robot with respect to an adaptive one. So after this first experiment, we also tested the system in ER, so with children waiting to be visited by doctor. And of course, in this kind of domain, we wanted to have a more objective way of evaluating the anxiety of the children. So, for example, we evaluated the so-called cortisol level that could be taken out from the saliva. And also in this case, we found that this adaptivity of the robot had a very huge impact on the stress level of the children while waiting for getting their medication. So we can adapt. We can have a very simple user model. I think a question, so let me see if I can read it.
Yes, you have a question.
Yeah. So,
can you see it?
Yeah, I have two computers. Yes, I can see
Okay.
it. So how do you convert that you use to quantify happiness? Actually, the one that you see here, it's not the automatic one. So in these plots, there are some output that coming from questionnaires, because we both had the automatic evaluation, but also questionnaires that were provided to the parents. And the parents were, of course, there to rate their perception, of course, of the children happiness, upset, or neutral. So in this plot, it's not the automatic one. The automatic one was at the beginning only to trigger the one of the two personality. And then these three measures were made before, during, and after through the use of questionnaires. And of course, that was the reason why in the second experiment we use the salivary cortisol, because of course the perception of the parents may be also biased by their relationship with the children, their perception of the somehow I'm a mother too, so I could be like more in anxiety myself, seeing my son in anxiety mode too. So in order to avoid this bias in using questionnaires with children, of course children cannot take questionnaires by themselves, we had the measure of salivary cortisol level. Which two personality the robot has? So the robot has two, I won't call it personality, but two different way of expressing emotion. So the main pattern of interaction was the same, like making jokes or asking questions. So there were this behavior, interactive behavior with the user, but the way the robot was giving this interactive scenario had like a very joyful in one sense, and a negative one, not in terms of anger. So the picture is just for fun, but in terms, for example, of sadness or frustration. So in one way, the robot was all positive in its emotion, and in another way was really sad or frustrated. So its own behavior was more on the negative side, or showing negative emotion with respect to positive one. Of course, we tried also with anger and other things, but at the end, the too effective one was the, let's say, the negative with low arousal, like sadness and joy on the other side. Okay, so in these cases, we had all the components. So we had the user model, we had the possibility to parameterize the behavior of the robot with respect to a user model and with respect to observation. But then we want more, because we want also that what the robot is doing should be adapted. So we want the application to be selected in a very dynamical way. So also the planning, let's say, of the robot should be personalized with respect to the user. So in this case, we thought, okay, since we taking a lot of inspiration of computer networks application like service-oriented application, why not try to use the same paradigm also for robotics? So what we would like to have is the possibility of designing what to do and then deciding in a dynamical way which is the best functionality to achieve the goal. Or changing, for example, the sequence of goal we have to do with respect to the current situation. So we want that this user modeling adaptation process will be taken also more from a decision-making point of view. So, for example, in the case of the elderly, this was the user model that we had. So we had, of course, personal data. We had data on the activity the user typically do during the day. And then we have also preferences. We have also the cognitive profile of the user, because it's important, because there could be different impairment, different memory issues. And then we have also the personality profile. So starting from this user model, we should be able to understand what to do and how to do in a dynamic way. And once we decide what to do, we should also decide how to do it. And also taking inspiration from the service-oriented approach, we thought of how to model the so-called quality of services within a function. So, for example, suppose that I can do the same function. I can do the same, like, for example, approaching the user, but I can modulate the parameters of the function with different quality of service. And the quality of service, for example, can be the intrusiveness. So approach closer or with more distance, or the reliability of the function itself. So different speeds, different movements, different modalities of interaction. So all these features can be modeled in the same framework as quality of service value that could be adapted and decided from time to time with respect to a specific user model. For example, suppose that, again, we have the robot that has to monitor what the user is doing. So we have actually the system has to monitor what the user is doing, and he have different things to decide. So, for example, he could decide to do this monitoring activity by relying on wearable devices. So, for example, wearable devices could be used for understanding what I'm doing, but typically they value are low reliable, because I can just typically recognize the pose, but not really activity. But really, it's good, low reliable, but it's also low intrusiveness, because we don't have the robot moving around. So we have these two values that characterize this function. Or we can have a robot approaching the user and asking, for example, to dialogue what you're doing. How are you? Are you watching TV? So again, it's a different way to do the same task, the same function, with a different modality. And in this case, of course, the result is high reliable because we are asking, but it's also high intrusiveness. And then we have, for example, a third option that could be not ask directly, but use the robot vision. So again, we have a medium reliability, but also a medium intrusiveness. So if I can do the same task with different function, I could choose the function that best fit the user model in this particular time. So actually what we had in the experimentation was the robot be in the user houses, and with the goal of performing different activities, different monitor activities, but also, for example, cognitive stimulation or entertainment at different times during the day. So the robot was able to wake up at specific time and decide what to do, how to do it, and with which quality of service. This is an example, for example, of adaptation of the decision-making of the robot. For example, let's suppose that we have the plan, the workflow of activity of the robot that, for example, was planned to detect the state of the user to the user wearable. And suppose that today I was not wearing a wearable. So the robot, the system is able to change the way to do it, for example, using the robot. Or suppose that the robot has to approach the user, but today, for example, I am nervous. So this observation can be used to change how the approaching is made in a dynamic settings, or if I'm really in a bad mood, I could decide to change some of the action with respect to the current state of the user. So we had this very complex system. Actually, we had this very complex system running in an autonomous way for almost a month in 8 different houses, or 7 different houses. So we have 7 patients enrolled for the experimentation, and you will see here that this distribution, it's very different in age, but it's also very different in education, in the type of memory impairment, but also in the familiarity with technology. And this was the average evaluation of the patients, of the behavior of the robot, and it was in a score from 1 to 3. So 3 is the top, 1 is the lowest. So you will see that here you have very good results with respect to these two that have very low results. And if you go back in this table describing the users, you will see that the one that gave the worst results were the one with the high familiarity with technology. So the one with very low familiarity were all very enthusiastic about the robot behavior. They all very happy to have, and indeed wanted to have more. Indeed, the one that had a higher familiarity with technology in general had a lot of expectation on the behavior. So a robot with very simple capabilities was not evaluated as good as what they imagine a robot could do. So in some sense, more I'm familiar with technology, higher are my expectations with respect to the behavior of a robot. The last 10 minutes I have, I would 5 minutes I have, I want just to talk a little bit about this other project, where, again, a lot of adaptation and personalization is involved. Why I want to talk about this one? Because this one is very peculiar, because it's not a personal robot, it's a service robot, but a service robot deployed to be used into the wild. So in a real bar where the people can go and buy drinks, the robot will be able to make drinks, but also to interact with them in a personalized way. And the goal of this robot was mainly to try to understand how to be engaged using this kind of user modeling and personalization to make the user engaged in interaction, and of course make them coming back later in time. And to do so, we had these two things that are called system of record and system of engagement. So two different modules that somehow keep track of past interaction and keep track of the current interaction, and use this data to adapt the behavior or the interactive behavior of the robot itself. Also, we rely on other disciplines, as I said. So we rely on recommender systems. So, for example, algorithms that I use for like Amazon or Netflix to suggest you what to do. So why not use this kind of algorithm also to make the robot able to interact the best as possible with the particular user. So the bartending scenario, it's extremely challenging, because typically a bartender is like a psychologist. So you typically go always in the same bar, so you know the bartender, you talk with the bartender know about yourself, what you like, what you want to do, what you want to talk to. So this requires a lot of user modeling in order to be effective during the interaction. So it's not just making drinks, but it's making the robot able to rely on this knowledge, getting this knowledge through time and using to personalize the interaction. So that's mainly how the robot it's built up. So it has a face, a very expressive face, because it's a full-art robot. Then it has two cook arms to make the drinks, but also have a panoramic camera here to recognize the whole environments of the bar, and also two arrays of microphone to get a better understanding of the natural language commands provided to the robot. So I'm going to skip the complex architecture, and I want just to show you the main components in order to personalize the behavior in the robot. So first of all, we need to detect the user, and of course keep track of the past interaction. So in order to detect the user, we need, of course, the user to be registered, but we also need to rely, for example, on biometrical data. So we rely on face recognition tracking, and even though the use of biometrical data is quite debatable in this period, we need to be able to recognize who I am talking to and how to retrieve all the data I have on this specific user. And so if I know this, I recognize the user, I can make personalized interaction, for example, suggesting particular drinks or suggesting news, in the sense that I interact knowing what you like to hear. And also I should be able to update my knowledge while interacting with you. For example, in the case of suggesting drinks, suggesting drink may work in different way. For example, suggesting bestseller, but also suggesting drinks that are similar to the ones you used to drink. For example, here we don't have drinks, we have like smoothies. So for example, understanding how the drink is made, the system is able, reasoning on a graph, to understand which other drink could be similar to the one you ordered before. And also the system is able to identify the current mood of the user through a multimodal channel, for example, to analyzing the tone of the voice, the frequency of the speech, but also the face, also the pose. So he has the possibility, since in this case we have a very clear view of the user, we can use this data to understand how to interact with the user, how the user is engaged, because this data, remember at the beginning of the talk, could be used to evaluate the engagement of the user, and also whether the user is alone at the bar or with the group of friends, because this way the interaction would be different. And for example, this could be used to change also the type of interaction. I will just finish and now I will reply to the other two questions because I'm almost there. So, for example, could be the seriousness of the interaction change. In the case I'm happy, it could be, for example, better to hear funny news or to hear regular serious news, or also how the robot should reply to a user should be personalized with respect to his or her current mood. And just example of different reaction that are verbal, different reaction, but also emotional reaction, different using the face of the robot. That's just a very small video of the user. So once the user is registered, the robot is able to have different conversation with the user while asking, for example, the drinks, the confirmation, and making different animation with respect to the current state. But is also able to engage in multi-party interaction, because we can imagine that we have multiple users at the bar. So the robot should be able to get the proper time taking within the user while customize each single interaction with respect to each single profile. So, concluding, what is the takeaway message? First of all, in order to have this data, to have the proper user model, we need to rely both of offline and online data regarding the user. And when we are dealing with online data of the user, there are very different perceptual challenges that arise, because we don't have any more face-to-face interaction. We can have very different angles to observe the user. So there are a lot of research also in this specific area. And then we have to understand that once we have all this information, they should be used in decide what to do. So in the planning process, for example, all the information I got to the user should be taken into account for providing the correct list of action to do, but also how to do it. So also, once I decide that I want to achieve a specific task, there could be many different ways, for example, modeling many different nonverbal cues of the robot that could be used to adapt the interaction. So I'm stopping here because I'm out of time, I believe. So I will just keep answering your question. So, Monica was asking which particular robot was inside the patient house. Actually, inside the patient house was not Pepper. Let me see if I am. Was this robot. This robot is called Sambot. And we, of course, choose this one for many different reasons. One was that one of the objectives was to have a low-cost device. So this is a low-cost device that could be used. So even though the multimodal expression capabilities are limited with respect to Pepper, the balance with the cost was more effective. Then Marta is asking, how did you tune the speed during the interaction? Yeah, okay. So in the first experiment, the speed was inversely proportional to the speed of the user, in the sense that if I'm countdown, so I'm totally aware of what the robot is doing and I'm making very slow movements, the robot is confident to, let's say, work at its own full speed, regular speed. While if I start moving too much, he has to slow down. So will be like an inverse adaptation with respect to the perceived velocity of movement, in particular of the hands of the user. And the adaptation of trajectory in this specific scenario were mainly about stopping or starting. And also, I didn't show there, but it was adapted with respect to the position of the user. So in this case, it was a simple predefined trajectory, but suppose that you have a robot moving around. You'll see in the paper there are a lot of details. The robot should adapt to respect to the current pose of the user in order to make the pick and place action, because the robot should be always in the visibility area of the user. The next one, 2 ways of personality for the robots, I suppose, to make something in the middle. Actually, the main goal was not to make something in the middle in this specific scenario, but was to get the attention of the children. Because once you are able to get the attention of the children, then you can keep it going in interaction. So the 2 personalities at the beginning were polarized in 2 different ways in order to understand if the dynamical selection of one or the other could get the attention better with respect to initial level of anxiety of the children. And of course, the long-term goal would be also to change this dynamically, because in the specific experiment, we had just the first selection at the beginning, but then our goal is to change during interaction, because I may be in a different way, I may change, or of course, natural interaction requires adaptation and changing. If I always behave in the same way, that's not natural. So a natural robot would be someone that changes. So you're right. And the main challenge to reach it is to be able to effectively recognize what is going on. So there are perceptual challenges, especially in this task. The next one, do you think going for a humanoid robots? No, we don't want the robot to replace the humans. Absolutely not. Also, for example, in our cases, the robot was an additional assistant of the caregiver. So all the user had his own caregiver, but the idea is the robot indeed also helped the caregiver too. So the caregiver, of course, we are not expecting him or her to be awake 24/7. So why not relying them to the real needs of the user, the personal human-human contact, and leave all the other repetitive stuff to the robot? So the idea is the robot is something to be helping the caregiver, as to be helping, for example, the trainer, to be helping people during rehabilitation. So it's an additional help that makes the worker more free to leave aside the repetitive stuff and concentrate more on the human-human interaction. And what about the human form? I would say it depends, because you see, for example, that in the case of elderly with high expectation, with high familiarity with technology, they were disappointed because they were expecting much more. And also the human form contributing in increase the expectation. So in some cases, it's better to have a very simple robot if their skills are very simple, because higher is the anthropomorphism of the robot, higher are the expectation of the user. So it's more easily to fail in this case. I don't know if there are, I don't think there are any other questions. Stop sharing.
Thank you very much, Silvia,